So, good afternoon, everyone, and welcome to this first webinar of our winter series on the design of electrical machine. It's honestly like a real pleasure to see the number of people attending today, and I really would like to thank you, all of you. And it's so nice also to see this continuous growth in the interest, of course, in the electrical machine design world. So, I am Giuseppe Volpe, an electrical machine specialist here at Model Design Limited, and I will take you through this webinar today, looking for an answer to the question, the electrical machine design is an electromagnetic problem. Um, let me add, is just an electromagnetic problem. So during the webinar, please feel free to type your questions in, and I will try my best to address as much as I can at the end of this webinar, but the question that do not get answered in this session will be answered after the webinar, so you will soon then receive a mail with the answer to your question. Just for letting you know, all the attendees are in just listening mode, so we cannot hear you from here. So if you have got any question, please just type your question in. So the topics of today and what we're trying to cover today is why is the multiphysics design and analysis in the initial stage of the design process so important? And for doing that, we'll carry out a comparison of design decisions based on multiphysics analysis against just the electromagnetic analysis. So we will have different designs and we will compare different solutions considering just electromagnetic analysis or integrating different physics behind the electrical machines. So before we start today, let me give you a brief introduction about who we are and what we do here at Model Design Limited. So Model Design Limited is a company founded in 1999. We're based in the United Kingdom, basically on the borderline between England and Wales. And the idea of Model Design Limited started to develop a tool, a software, focused on the design of the electrical machines. So we can now count on 470 companies worldwide using our software or our consultancy services. We got customers in 30 different countries and across the 6 main industry sectors like automotive, aerospace, rail, renewables, and so on. Here we do a lot of research, so we really believe a lot into research work. That's why we got 26 partnership with universities worldwide, and that's also why a big slice of us has got a PhD in the electrical machine design. In addition to that, we got partnership with the 5 major engineering design software developers all around the world. First of all, what we do here at Model Design Limited is to develop MotorCAD. MotorCAD is a multiphysics software for analyzing and designing electrical machines, electric motors in general. So we do believe a lot into the interaction with our customers. So we try and invest a lot of time in understanding the requirements of our customers. We try to help a lot in the initial stage of the design process, or also when new customers try to understand how MotorCAD work. In addition to that, we also offer consultancy services, so we can provide design, studies, or analysis and training about electrical machines. And as I was saying before, there is a big slice of us who is focused exactly on the electrical machine design. In addition to that, we're involved in several European-funded research projects and in UK projects, and we collaborate again with universities worldwide to develop electrical machine modeling techniques, basically. So MotorCAD is a software that we pretty much covers all typical types of radial flux rotating electrical machines. So here you can see a few pictures about MotorCAD, like the 3D view, or the flux density, or the efficiency maps, or the slot temperature distribution inside, inside windings, inside slot. And we can study different kind of machines. So brushless permanent magnet machine with inner or outer rotor, induction machine, synchronous switch reluctance, synchronous wound machine, and so on. And the power behind MotorCAD is that it's not just the conventional full FEA, so full finite element analysis tool. Actually, what we try with MotorCAD is to use a combination of analytical and numerical modeling techniques in order to get accurate results, but faster. So we want to get, in a short time, accurate results in order to get an easier design process and a faster designing process, also for additional optimization. So let's get to the question. Electrical machine design is just an electromagnetic problem. So traditionally, electrical machine design has been seen as a problem which can be solved just using electromagnetic analysis. Or we can say that electromagnetic analysis is seen as the primary tool required to do electric motor design. However, as we increase performance demands and there is more competition in terms of different motor design, we have to try to push the design limits in terms of electromagnetic, electrical, thermal, and mechanical performance. A lot of the decisions are made when we start the design, so at the early stage of the design process. So really what we need to do is to try to understand how our electric machine design performs, not just in terms of electromagnetic behavior, but in terms of the multiphysics behavior, right from the early stages of the design concept. Why we need to do that? So basically, this allows us to make correct decision and create very competitive design that have much lower chance of problems occurring later on. So we don't want a process where we start the electromagnetic design, optimize the electromagnetic design, and then find that it, for example, gets too hot in the winding, or the magnets get too hot, or for example, that it is mechanically not strong enough, or there are other bits of behavior that we didn't consider during the early stages of the design process. So, as well as the design process, also the optimization is nowadays a very big thing, because we really want to try to optimize our machine. And a lot of the electric machine designers are automated design optimization to set the design variables for their machine. But the point is that even cutting edge design and optimization methodologies tend to use only electromagnetic design in the optimization loop. So here, for example, here on the right, you can see these graphs taken from a recent publication, basically in 2016, which represent a modern cutting edge design optimization procedure. And you can see here that they do basically the large scale design optimization, performing only electromagnetic optimization to evaluate the design parameters. The multiphasic performance validation is performed just right at the end of the process. So after we performed our optimization, we just check with the multiphasic analysis that the machine is behaving as we are expecting, basically. So we are not really performing a complete optimization on the machine. So this is where basically our MotorCAD philosophy comes from. So if we imagine if we try to include all those things, not just as, let's say, an additional stage, but actually we put them in the optimization, or for example, in the design loop as we are making these design decisions. And for example, we are changing things like the machine parameters, for example, I don't know, the tooth width or the slot depth or the magnet dimension. We want to know how that change is going to affect the electromagnetic behavior, but also how it is going to affect, for example, the thermal behavior of the machine, and which is, for example, the impact of that change on the continuous torque speed curves. And I don't know, for example, how it's going to affect the stress on the rotor as well. So what I want to show you here today is how bringing this analysis forward into the design process, we can actually make better decisions. And these are not like insignificant. They're quite different in terms of the design choices you would basically make since the early stage of the design process. So let's start with quite a simple example. So starting to consider the coupling between the electromagnetic and the thermal modules. So without early stage thermal analysis, generally and typically in designing routines or optimization procedures, what we would do is to rely on the current density. So we basically set a maximum current density value in the winding that, for example, here is considered as 10 amps per millimeter squared. And here we get exactly two designs. With these two designs, I've got exactly the same rotor, but different number of slots. The shape of the slot is different as well. So with 10 amps per millimeter squared, we basically calculated the electromagnetic behavior for these two machines. So on the left, we got a 48.8 IPM machine, and on the right, a 12 slots, 8-pole machine. So we calculated the electromagnetic behavior, and both of these designs produce very similar amount of torque. So both of them are able to deliver 275 Newton meter. So let's say from an electromagnetic perspective and from a design optimization perspective, actually these two designs are pretty much equivalent in terms of their electromagnetic behavior. However, when we couple these two things together, so the electromagnetic behavior and the thermal behavior of these two machines, and we compare these two machines, we will get something slightly different. So let's consider to simulate and to consider the same operating points for both these machines, both equipped with the same cooling system. So here I'm considering a water cooling jacket. And coupling the electromagnetic model to the thermal model, so what I'm doing here is running different iterations for getting the correct temperature inside the machine. So basically what we see is that the 48 slots and the 12 slots design are really not equivalent in any way. So we can see that the shape, for example, of the slot has a massive impact on the thermal behavior of the machine. In point of fact, here we can see that the temperature in the 48 slot machine is 145 degrees against the 171.1 of the 12 slots as average temperature. Meanwhile, the winding hotspot is 156.1 in the 48 slots configuration and 216.7 in the 12 slots one. So there is more than 60 degrees difference in temperature, which is really significant in terms of performance. And we could never really claim that these two designs were even close to be equivalent. So this first example, let me say, is quite easy to generate and shows that designing a machine just considering a fixed current density, so in this case 10 amps per millimeter squared, is not enough. So if the current density also is the same and the electromagnetic behavior is the same, it is actually not correct. And actually it kind of, let's say, undermines a lot of fundamental assumption that is made in the normal design optimization procedure. So as next, what I want to do, we can move on to the designing for field weakening behavior, which is another commonly used designing procedure. And we're going to design a so-called 1 per unit inductance machine. So For a very long time, it has been considered as a design rule, or let me say, as the design rule. That means that when we design our machines, we aim for a short circuit current equal to the rated current or to the continuous current. This is what I mean when I say 1 per unit machine. So here on the right, you can see different papers and ranging from 1990 to 2005. Basically, they are reporting from different points of view the same idea. So we need to design a 1 per unit inductance machine. The reason for which we do this is because uh, the 1 per unit inductance rule is basically a clear trade-off. So if we go for very high short circuit current, we can get very good peak power and inverter utilization. But the machine basically cannot operate continuously at high speed because it gets too hot. On the other hand, what happens is that we can have a very low short circuit current leading to a good thermal behavior of the machine at high speed, but a not so good utilization of the inverter, as well as in terms of peak power of the machine. And this design rule kind of gives us a good trade-off between those two issues. In automated optimization procedures, generally, this is used to constrain something, because if we don't constrain something in our optimizer, basically the optimizer kind of runs away, maximizing the output power, for example, but on the other side is limiting the machine thermal behavior at high speed. So this is a general design rule, and using electromagnetic analysis only, this is basically what we have to do. We have to apply some kind of design rule, a constraint, for example, on the short circuit current, to make sure that we have got a design that is basically able to operate thermally. But my question now is this enough? So here I've got a design which is a typical 48 slots, 8 pulse IPM machine. It is the same as the one used in the first example, and it is designed basically with that rule in mind, so the 1 per unit design. In point of fact, the short circuit current is 230 amps, and the current density is around 10 amps per millimeter squared. So using, again, the water jacket cooling system as before, we can actually check in MotorCAD the winding temperature, which is, we can check the winding temperature, which basically is 160 degrees, the average temperature in the winding at 500 RPM. So this is definitely a design where the continuous current is equal to the short circuit current. We have a maximum current from the inverter of 500 amps, so roughly double the continuous current. And from a typical electromagnetic perspective, or even using this initial coupling between electromagnetic and thermal, this design, we can say that looks actually pretty good. So it matches the performance requirements, the current density is reasonable, and the low speed thermal behavior of the machine is good. So I could say this design is good enough. But when we actually do with MotorCAD, what we do in MotorCAD is not just to have a look to the electromagnetic and thermal coupling, but we can bring what is so-called the lab model into it, which allows us to basically use a control model and have some advanced losses calculation. This includes a lot of details like uneven distribution of the AC losses in the slot, the variation of the AC losses, I don't know, with the temperature at different operating points, or for example, how the torque is varying with the magnet temperature, and how, for example, we change the control strategy based on the back EMF that we know is function of the magnet temperature. So we can use this calculation to make a better design of the machine, coupling it with electromagnetic thermal models, but actually also solve continuous thermal envelope basically across the full torque speed range. And this is actually what we're going to do now with our design with this 48 slots 8 poles BPM machine designed with a 1 per unit inductance. So here we can see the calculated peak torque. We can see the continuous torque, peak power, and continuous power. Unfortunately, when we calculate them, we discover that although we've respected that initial design rule, in this case, basically the machine is actually getting too hot at high speed, and our continuous power and torque basically falls to zero at 9,000 RPM. So here the torque basically is zero. So effectively, this is showing us that we cannot operate above 9,000 RPM without the machine getting too hot. The reason behind it is that the current basically is not the only effect to consider, since it is not the only source, the only heat source inside the machine. So there are loads of other losses components inside the machine, like for example the aero losses, the AC winding losses, or the eddy current losses inside the magnets, and loads of other small things that basically end up with this machine that is not able to operate continuously at 9,000 RPM. So it is basically a much more complex interacting phenomenon that the one considering by just, the fixed current density, so that simple design rule. Without having detailed coupled models together, we actually wouldn't be able to see this behavior. It might be that this is limited, for example, by a constraint on the rotor temperature, for example. So we need to figure out how to reduce the magnet losses, or how we need to change the cooling system of the machine. So it's important to understand since the beginning what we need to do for getting this machine able to work. Let's consider now another example. So looking again at this 1 per unit design rule, in this case, here I've got a slightly different design. So here I'm considering a 24 slots, 16 poles machine, which is, let's say, common IPM design. And again, we've designed this machine for a 1 per unit. So here the short circuit current is 270 amps, and the current density is again 10 amps per millimeter square. Considering again the same cooling system, so with a housing cooling jacket, the average winding temperature achieved here is 160 degrees. So bringing the lab module in and performing similar analysis as before, we obtain this performance. So again, in blue, we can see the peak torque and the continuous torque, and the peak power and the continuous power here. And when we calculate this continuous performance, actually, they look pretty good. And the 1 per unit design rule, in this case, has worked well. And it is giving us a design that operates firmly at the maximum speed. So we can see here that at the maximum speed, we got pretty much 80 Newton meter. We can deliver pretty much 60 kilowatts. So the continuum torque shows that the design can operate all over the speed range, and we can get a very good 60 kilowatts at 7,000 RPM. So what I want to show here is that in this case, the design rule seems to work well. Meanwhile, in the previous design, wasn't working well. So is it enough just to consider that design rule or not? So here, what I've done, I've taken that design, I played a little bit with this geometry. So I increased a little bit the stator bore, I open up a little bit the slot, I change a few parameters as shown here, but keeping pretty much all the other design parameters consistent. consistent, sorry. So including, for example, the slot fill factor of 0.5. By doing this, what basically I did, I raised our short circuit current because I'm increasing the saturation level, of course, inside the machine. And so now the short circuit current is 370 amps, which means a 1.5 per unit design, which corresponds to a current density of 15 amps per millimeter square. If we now look to the temperature behavior, we see an average winding temperature of 350 degrees at low speed. So there is basically no way that this design would respect that initial design rule of short circuit current equal to the rated current. In this example, in this case, my short circuit current is quite above the rated current. So if we were designed with the 1 per unit constraint on the short circuit current, we definitely wouldn't never ended up with this kind of design, which for now looks a little bit kind of crazy. However, if I do, as we did before, a calculation with MotorCAD using the coupled electromagnetic, thermal, and lab calculation, what we can actually see is something completely different and, let me say, also unexpected on the continuous performance. The new machine performance looks pretty good, and it is actually quite even slightly better than the 1 per unit design that we were doing before. So this clearly goes against the conventional design rule, and the biggest difference here is on the peak power improvement. So before I said that this 1 per unit design is a good trade-off between continuous performance and peak power. But in this case, we've increased our peak power by breaking this design rule. And we have actually obtained a design that looks very good, actually, and even more capable in terms of producing continuous torque at higher speeds. So clearly, this design is much more competitive than the previous one, and I basically broke the design rule that I was telling you before. So effectively, we need to push these design limits, and we really need to understand this complex interacting phenomenon of the coupled analysis. So without doing this, we're going to have designs that, for example, ended up with problems like the one before, that, for example, problems we didn't initially consider, or we have design which are not competitive at all. So really, to find that limit out, we need to understand which are the trade-offs, and we need to do this full coupled electromagnetic, thermal, and lab analysis. So, but there is still something missing. In this final example here, I want to bring in also the mechanical analysis as well. So as people generally know, designing the rotor of an IPM machine is basically a trade-off between mechanical stress and electromagnetic behavior. And it is actually pretty crucial, in particular when we, of course, try to push the machine design to higher power density, increasing, for example, the rotor speed. So typically, what we do in a design process, we optimize the electromagnetic design. So we, for example, might set some limits in terms of bridge thickness to try to make sure that the design is mechanically realistic. So then we will probably send, let's say, our design to the mechanical team, or we perform the mechanical analysis at a later stage. So again, is like that first optimization process I was talking about before. So we optimize the design electromagnetically, and then we study the mechanical behavior of the machine. So here I want to consider the mechanical behavior, let's say, in parallel with the electromagnetic one. So considering a slightly different slot pole combination, so here I'm considering a 72 slots, 12 poles machine. So we want initially to figure out which is basically the trade-off between the electromagnetic behavior and the mechanical stress. This is quite important, particularly because the machine designs nowadays are pushed to higher power density. How? Basically, you can do that by increasing the rotor speed. So in this case, I'm going to consider this machine, so this 72 slots 12-pole machine, and study which is basically the effect of the V angle on the mechanical stress, as well on the power and, let's say, power and torque performance that I'm going to show you later. So when we vary the V angle from 90 degrees to 180 degrees, the first thing that we notice is an impact on the maximum deliverable torque of the machine. So on top here, we can see two of these cases, and in the graph, basically, I'm plotting the torque against the rotor V angle. So we can see the torque variation versus the rotor V angle. The torque here is clear, can be maximized with 120 degrees V angle. And after this value, the torque starts to follow, giving up to 100 Newton meter difference. So for example, the torque at 150 degrees is 18.5 Newton meter lower than the one at 120 degrees. Hence, just considering the electromagnetic performance of the machine, in addition to the V angle, we would end up saying that with 120 degrees, I am maximizing my output torque, so I can choose easily 120 degrees as the angle, so which is basically the angle between these two magnets. But when we bring the mechanical calculation in and we consider the electromagnetic mechanical situation with the maximum mechanical stress acting here on the rotor bridges of the machine, we see that using 120 degrees V angle, the mechanical stress is about 440 megapascal, and this value is above the maximum allowed one. However, if we consider 150 degrees V angle, we ended up with 375 megapascal as maximum mechanical stress, which is still above the maximum allowed stress, but is lower. Therefore, if we want to keep the maximum deliverable torque by the machine, what we need to do is to reduce the maximum speed at which the machine basically can operate. So for example, this machine that I'm considering here can safely operate up to 10,000 RPM with a V angle of 150 degrees. So we can say, right, I'm not pushing to the maximum speed of 15,000 RPM. This machine, I'm reducing the maximum speed to 10,000 RPM. So basically the torque at low speed is going to be exactly the same. But in this way, what I'm doing, I am sacrificing the output power of the machine. So as I said before, the output power of an electrical machine is strictly related to the machine speed. So since the power is the torque times the speed, of course, the output power is related, of course, to the machine speed. So in order to increase the maximum machine output power, and so to increase, of course, the power density of the machine, we can consider to push the machine to higher speeds. When we do it, we need to check, of course, the mechanical integrity of the rotor. And this is basically what I'm trying to do here. So I want to push the machine to the limit. And what I'm going to do is to increase the speed of the machine, and accordingly to this, increasing the rotor bridges thickness in order to do not exceed pretty much 300 megapascal on the bridges. So here on the bottom of the slide, you can see the bridge required for running at 8,000 RPM. So here, basically, I'm fixing to 150 the V angle, and I'm calculating and estimating the bridge thickness in order to do not exceed 300 megapascal. So here at 8,000 RPM, I've got these bridges. For getting the same, pretty much, stress, at 20,000 RPM, I need, of course, bigger bridges as before. So from this study, it's possible noticing that the power, which is the blue line here in the figure, goes up with the speed, reaching the maximum at around 20,000 RPM. The rate of increment is quite high, from 8,000 RPM to 15, let's say 17,000 RPM. After this point, the rotor bridge starts to have a really important effect on the flux linkage, and so on the generated maximum torque and power that we've got. So as a result, there is, let's say, a kind of optimum value after which it is not worth increasing the speed anymore. So I can see a really nice and big improvement on torque going from 8,000 to 15,000, 70,000 RPM. And of course, if I increase a little bit the speed and I get a big difference in the power, is worth. But for example, up here, so between 70,000 and 20,000 RPM, I'm increasing the speed, but my power is not increasing that much. Of course, in addition to this, we need also to consider that when we increase the machine speed, for example, so let's imagine that we're considering like a car. So we got a fixed speed of the car, so a fixed wheel speed. If we increase the speed of our electrical machine, we will need a bigger gearbox, because of course the speed of the car is going to be the same. If I increase my electrical machine, electric motor speed, I will need a bigger gearbox, which is going to be heavier. So in this case, it's important to think that if I have just a small increment on the power, it's probably not worth increasing the speed anymore, because I'm making the system afterwards more complex. So that's why the whole thing comes together. And that's why, for example, in this case, I wanted to show you why electromagnetic, thermal lab, so the control and the mechanical coupling, must be performed since the early stage of the design process. So what we have shown today is that using the electromagnetic analysis for making design decisions turns to lead to suboptimal solutions, or solutions that may result in problems at a later stage of the design process. And actually, these are not like minor things. They're not small little things that we can neglect. They're actually making a huge difference to the way we choose our design parameters. And really, a coupled solution involving electromagnetic, thermal, and mechanical, and also the control models is the only way to properly explore and evaluate the entire design space. So this basically allows us to make better decisions, to generate competitive design, and gives also advantage in terms of machine designers. So it is less likely to design problems at later stage of the design process, when it can be quite costly to fix what we got wrong. So here, what I wanted to show is the interaction between all the physics basically behind an electrical machine. But I leave you today with, so I started with a question: if the electrical machine design is just an electromagnetic problem, and hopefully I've answered that during this webinar. But I leave you with another question: where do we go from here? So now that we got the idea that, of course, we need a couple to study the full interaction and the full phenomenon happening inside the machine, where do we go from here? So how we can properly account for all these aspects into the design process or in the optimization procedure in a practical way. So The answer to this question will be given and covered in our next webinar on the 4th of December 2019. You can reserve your place going on our website. And yes, so thank you very much for attending this webinar today. And you will receive the link for the records soon about this webinar. And I'm happy now to answer your question. So let me, okay. Let me just try to figure out and to pick up some question. Okay, let's start from this question from Andrea. So in several slides, you speak about continuous performance of the machine, how they're calculated. Okay, okay, let me go back to the slides. And yeah, so I think Andrea is referring to, for example, let's take this one. So the continuous performance. So here, what I mean with continuous and peak performance of the machine, of course, when we speak about peak performance, so peak torque and peak power of the machine, we're considering the machine operating for a few seconds. Okay, so we just want to check that the machine is not overheating, for example, for 10-30 seconds. When I speak about continuous torque or continuous power, so in general, when we speak about continuous performance of the machine, we of course are considering points, let's say, in which the machine is able to work, let's say, ideally forever. And in MasterCAD, how we do that? We do that basically calculating, we start from an initial suggestion on the current. So we calculate the temperature inside the machine, considering that initial current. And then we iterate, increasing that current until we reach a point in which, for example, we don't want to exceed a fixed temperature inside winding or a fixed temperature inside basically the magnets. So hopefully it's clear. So basically we do like the iteration. Actually, I was looking before, there was also a question on the iteration, so which is strictly related. So let me take that now. So before I was, when I was speaking about the thermal iteration, I was speaking about the iterations that I'm doing for getting the machine performance, so for getting the temperature inside the machine. So what we do there is basically starting from a current, we calculate the losses with that temperature, and calculating that losses, we calculate again the temperature inside the machine. That the new temperature is updated back in our electromagnetic model, and automatically we recalculate the losses that we know are going to change with that is going to change, of course, with a different temperature. So we do pretty much few iterations before getting to the point. So let's see. Okay. Was it the same number of winding and number of turns? So Mohammed asked, I think he's referring to the machine. So basically, when I'm doing the comparison, I'm fixing the number of, I'm fixing the current density, and I want that maximum torque, that maximum power. So I'm of course adjusting that based on the number of slots, because of course with different number of slots and poles, I cannot really keep exactly the same number of turns. So I'm basically adapting that in order to fixing that current density, get the same performance. Right, let Let me see if there are both IMAG thermal. Okay, so Arvind is asking if MotorCAD does both electromagnetic thermal and is possible to do. Okay, so he's asking if basically we can do CFD analysis as well in MotorCAD. So the power of MotorCAD, so we don't do basically CFD analysis in MotorCAD because what we do, we use a lumped circuit thermal parameter network. So basically we developed this model in pretty much 20 years of Motor Design Limited and MotorCAD. So the idea is, instead of using complex CFD analysis, what we try to do is we figure out a quick way of analyzing electrical machine based on resistance, capacitance, and so on. And only in this way we can basically, so here, for example, you can see just a view of that circuit, but basically the idea is that we want accurate results, but we want to study, for example, drive cycle or duty cycle. And of course, with CFD analysis, in which each operating point takes a big amount of time, would be pretty much impractical to perform such a kind of analysis of simulation. So in MotorCAD, we basically study this design in this way, and then based on that, probably at the latest stage of the design process, you can probably build a CFD analysis for double checking the thermal behavior of the machine. Okay. Yeah, so how we can include probably everything in the optimization procedure, as I was saying, telling you before, is going to be covered in the next webinar. So we will show you an example on how we can optimize a machine, considering all these different aspects of the machine inside the optimization procedure. And yeah, I think I got time for another question. So let me just have another look. So okay, so how we can, okay, yes, so CFD. Okay, so let's take this other one. So Garin is asking about drive cycle and duty cycle analysis, how we can do that. So I didn't include any drive cycle analysis in here, but thanks to lab, so thanks to the control model that we've got, we can imagine to study basically and to analyze the electromagnetic behavior of the machine during, for example, a duty cycle. So let's imagine, for example, an electric car. So we can study a typical drive cycle, which is already inside MotorCAD. So for example, a US 06 or WTP or whatever. So we can first of all study the electromagnetic behavior of our electric motor during that drive cycle. And then based on that drive cycle or on that duty cycle, we can basically get the losses and the losses distribution inside the machine, and then we can run a thermal calculation over the drive cycle, which can be 1, 10, or how many we need to get, for example, the steady state. And so we can understand how the machine is reaching the steady state and which is the temperature, not in, of course, a single operating point, because if we're speaking about, for example, an automotive application, it doesn't really make sense to study a single operating point forever. So in that case, of course, we want to study a drive cycle behavior, as Karen is suggesting. And of course, we can first of all study the electromagnetic behavior of that. So we need to get, first of all, the losses inside the machine. So we first of all build the so-called efficiency map, and then we calculate the operating points in which the machine is going to operate over the drive cycle. And then after we get our losses, we automatically link it inside MotorCAD Thermal to the thermal module, and so we can run our lumped circuit parameter, so the one I was showing you before, and then we can, of course, understand the temperatures inside the machine, in each part of the machine during the drive cycle. So, uh, thank you very much. There are loads of other questions, and I will try to answer soon. So we will try to give you an answer as soon as we can. I really thank you very much for attending this webinar today. Soon will be available a record of this webinar, and if you liked it, just join us next week for the next step of the electrical machine design process. So thank you.